buzzing in the back of the room. If you built a machine that worked a little bit faster, it'd already be done. Just kidding. Just kidding. Actually, I know a bunch of people were enchanted by the machine. The machine that's actually milling the board back there, I purchased better part of about a week and a half ago. I wrote a review, which is up on a website, the blog site, which is just spy.vibrating.com. Purchased it outright. He didn't bait me with anything. I paid cash for it, but I've had nothing but fun with the machine. I wish I would have bought that before I bought something like a MakerBot or anything like that. It's not my first rodeo with milling machines that I've managed in the last 10 days to mill out 6, maybe 7 PCBs out of it with pretty good resolutions. It's a really cool little benchtop machine, and that's 6 or 7 PCBs with 10 mil spacing on most stuff. Good enough for most QFPs. I can't get into some of the finer FPGA packages, like chip scale packages and stuff like that. But I've had a lot of fun with the machine. I've rocked it for the last like 10 days or so, and I've built some circuits that work in a reasonably short amount of time. 3 hours, 4 hours, something like that, which is a lot better than waiting 4 or 5 days. Anyway. Chris is trying to nudge me to not tell my life story when it's really Mike's opportunity. I just had this habit. Anyway, so check out the machine in the back of the room. I was really excited when he agreed to actually give a talk. So that said, afterwards we've got Josh talking about FPGA core design, specifically designing SPI cores for FPGAs, which is really cool. I'm eager to see. I'm actually eager to see his code. Anyway, so without further ado, this is Mike. There's some further ado. Oh, there is some further ado. T-shirts. Yeah. So we've tried many times unsuccessfully to give away things and try to do that when we had few things, but many people. We've got some T-shirts in the front of the room. If people are interested, pop up here later on, and whoever attacks the box first actually gets them. So we'll do that at the end after Mike and Josh both had an opportunity to talk. So cage match. Yeah, exactly. Just fight your way in, grab a shirt. Yeah, it'll be cool. Anyway, awesome. So Mike.
So can everybody hear me okay? Cool. So Chris invited me to come and talk about CNC machines, and I was trying to figure out what to talk about because it's kind of a broad topic. And so what I thought I'd do is I thought I would tell you guys the history of how I became a machine designer, which is not really something that I set out to do. This is my first mill. I got it in 2004, and it's a tag mill. It's pretty heavy. It's about 70 pounds. It's pretty awesome. Like, you can cut steel with it, and it can do it at a pretty decent clip. It's a benchtop mill. I wouldn't call it portable because it takes 2 people to move it. I tried to move it once and threw my back out for a couple of days. But I spent a lot of time getting this mill, and when I first wanted to get into machining, I went out on the internet and I'm like, what's the best benchtop mill? And did Google, and it came back with Shoreline and this one here at the time. And I liked the heavier construction on this, and so I got this. And then it arrived in a little crate, and the mill itself was, I think at the time it was about $800 or $900 or so. And I was like, yeah, I'm going to do this on a budget. And I quickly discovered that when you get into CNC machining, you really are getting into the bracket of the month club. And the first thing you have to figure out is how to put the machine together, because it comes broken down and it's not lined. And so you have to do something called tramming, where you take out a little indicator and you make sure the little dial's in the right spot. A couple hours later, you're like, yeah, that's probably pretty good, but I can go over it again. And then you have to figure out how your drive controllers work. And I didn't know anything about motor controllers at the time, so I could go on the internet. It was like a cheap motor controller. There was all these DIY ones, and eventually I was like, maybe I don't want to do that for my first mill. So I got some Deco drives. And to control the mill, who here has used milling machines before? Pretty much everybody. So you've all heard of G-code, which you need some sort of like control system to translate into PWM symbols. And the timing of those PWM symbols and their relation to the timing of the other PWM signals from different drives determines how well the machine will cut. It's one of the many variables that determines how well the machine will cut. And for the longest time, the way that mills are controlled is you use a parallel port. Yes, that ancient piece of technology with a bunch of pins out the back, and you need a real-time operating system or something that can be faked into a real-time operating system. And a tight little loop just goes and bangs out the timing. And so to get it into the drive controllers, we need this thing which is called a parallel port breakout board. You also need a power supply and an ancient Dell. That's the thing that I found in the dumpster that I used for it. The controller that I was able to get to work best was this thing called Turbo CNC. We'll get into that in a moment. So one of the things that I learned early on when I first got into machining is, unlike picking up a sketch pad and drawing a picture, you really have to have something that you're trying to make to properly learn how to do machining. Otherwise, it's kind of just frustrating. You can't really doodle in metal or anything. And so the project that I got this thing for was, my next door neighbor was this guy named Paul Plummer, part of Cycloside. And one day, we're sitting out on the front porch and I get to talk to him. He's like, "Hey, Paul, what you up to?" He's like, "I'm building a bicycle Ferris wheel." It was a bicycle Ferris wheel. I had this project called Star Wheel, which is a 3-person bicycle that you ride around in the middle of. You can see the seats here. And he wanted it to be illuminated. And in 2004, there weren't really a lot of options if you wanted color changing fixtures to illuminate something. They certainly weren't any that were battery powered. And so I designed this little small 4-channel RGBW color mixing fixture that's DMX controlled. And I machined the cases and did the firmware, laid out the board, built the heatsink, and wrote all the code for it. It sat on both sides of this Ferris wheel. In the process of doing this, I had to figure out how to get all the pieces to fit together into the enclosure. And because I was hand coding all of my G code, it needed to be fairly simple. I did the design in a parametric CAD program. Everybody here knows what parametric CAD is? Yes? I see a lot of nodding. I designed it in this parametric CAD program called Pro Engineer. And I got a student's copy, and so it was like $300. And I made up these beautiful CAD models about how the whole thing was going to fit together. And I was like, okay, well, now how do I get the machine to do anything? I didn't have a like HSM works or anything to sort of generate the G code. So I had to type it out by hand. And one of the things that you learn about what makes a mill easy or not easy to use is that if you can't bridge that last gap between your CAD and getting the machine to do what you want, you're going to be typing a whole lot. That's 693 lines of computer-generated code. The files that I would write using Turbo NC had to be banged out on this little DOS program, and they maybe got to be about 50 to 100 lines. There's no looping in G code, so if you need to repeat a line, you go and copy it and then edit it and copy it again. And this was my first experience with CNC machines. I looked at some other programs for controlling CNC machines. This is Mach. This is a very recent version of Mach that you can't tell from the interface.
90s or what?
It's really designed for a person who is a trained machinist to operate. And it's got all the knobs and all the dials, and it assumes that you have already been familiarized with some larger CNC machine. So if you're coming to it from, let's say, a Haas controller, it's just as friendly. I also tried Lick CNC, this is a pretty recent screenshot of it, and this runs pretty well. It gives you visualization. It's very hard to set up. It requires that you have a pretty intimate knowledge about all of the timings for your drive controllers, all of the pins. I had a lot of trouble getting it to generate clean signals coming So that was my first CNC machining experience, and I made a couple of projects with it. Had a pretty good time, and then it sat in the garage for a long time because the amount of work that it would take to just get the machine to the point where it was cutting was several hours for like a 5-minute cut. And so we had to set up the blocks, measure the stock on the bed, and check the dial indicators, and retram the machine because maybe it went out of out tune. And so it was pretty frustrating if you just had an idea and you wanted to get something out the same day. Machine number 2, I got this hand-me-down laser. This place I was contracting just got a fancy new $250,000 laser cutter. And this one, which is a 120 watt CO2 laser, was hanging out in the corner. And I was like, hey, looks like it's just taking up some space. I'll take it off your hands. And the lab owner was like, well, I don't know if I really want to let it go just yet, but why don't you hold on to it for me? And as everybody here in the Bay Area knows, that's code word for you'll never see it again. So we wasted absolutely no time at all. And I got a bunch of my friends hop on their motorcycles, and we rented a truck, and we had that thing out the next day. And before anybody changed their mind. And I was like, wow, this giant laser cutter. And first thing I did was cut a test cube with it. And if you look at that, there's something wrong with it. So this is where I learned the first thing about owning a CNC machine is that often you end up being a CNC machine repairman all of the time. And so this free laser cutter, the first problem it had was what you're seeing here is in a laser cutter, there's no force resistance on the work material. All of the force that you run into is from the gantry and the cutting head. And so the dynamics of the system need to be designed to capture that. And when you take a right angle turn, you have to come to a stop in one axis and then pick up and start moving again in another axis. And you can't do this instantaneously. It's impossible. So there's a deceleration and then an acceleration as it goes around cues. And the problem here was that the laser controller was a piece of crap. And the PWM driver had stopped varying the power output of the laser. So as the laser slowed down, the power stayed the same, and it would start to catch fire. And then as it picks up speed again, it would stop cutting. You'd see these like thin marks right in the middle here where it would leave stuff out. And we were scratching our heads over this because we didn't really know that much about lasers. And then we got this cut pattern. And you're laughing, so it means I don't have to explain why this is hilarious. So as it picked up speed, sure enough, you'd start seeing like ringing as it would go around the corners, and as the gantry would start to drag. And we eventually tracked that down to some ancient drive belts that had stopped really working. The name of the laser controller was the Top Wisdom Laser Control. And in trying to find information on the web, when I would type it in, I found stuff that was really relevant to sort of the process of using it. It was extremely painful to use, and I was trying to remove the thing. So I think this was probably the most relevant bit there. See on the teeth. And I found a great company called it's called Light Motion. It's up in Sacramento, and they sell imported Chinese laser cards. And so the first thing that we did was to rip out the guts of this free laser cutter and spend about $500 on the CNC controller and replacing its guts. It's also 220, and because it's from China, and I don't have 220 in my warehouse, so I had to change all the power supplies. I had to replace the laser power supply because it wasn't PWM anymore. The gas springs broke, and then the 150-pound metal door would come slamming down on people. We replaced the laser tube because if your chiller is on the fritz, and you start running your 120-watt laser, which is actually probably closer to like a 100-watt laser, 150 watts, it doesn't last very long. New optics, worked the optics out a couple of times, got a new blower, and replaced the drive belts, which was super fun to do because there were no specs that were in English anywhere in this machine. I have some screenshots of the silk screen of the old controllers to try and map the whole thing out, and it's all in Chinese. And I tried putting some of the characters into Google and seeing if I could get them to translate them. But I noticed that there's a really big difference between the terminology used in Chinese electronics and the terminology used in Western electronics. And so trying to find for something that was like ground, they don't use the word ground apparently. And I was never able to figure out what the word actually meant. So eventually we got it working and made some art, super awesome. At the time I didn't have a job, and so I was sitting at home in my underwear drinking a beer at 3 a.m. in the morning, sitting there with CAD and just like dropping the files into the control software and making a lot of art. And it was super fun. The design time between like when I would come up with a concept and then like when it would come out of the machine was the opposite of my experience of using a mill. Like it was, you could turn like 5 rows in an afternoon. Had some friends that built some art with it. This is a pixelated cloud, which is raining on someone's parade, literally. It's from a thing that happens in the desert. I had a lot of fun building flying robots. This is the top of the Eureka sand dunes. And I learned a very important thing about lasers, which is that you really need to check the materials. And if you don't, bad things happen. And this one is made out of ABS. Anybody tell me what happens when you catch ABS on fire? You get, what's that? Thank you. No, you get cyanide. And when it smells like almonds, it's too late. So eventually I figured out that the gas coming off of this stuff when I was cutting it was actually really horrible. Now I have an ABS allergy, but that was a fun learning experience. Speaking of rapid iteration and flying machines, this is a set of flying cardboard robots that I made. And I got really into working with cardboard. This is going somewhere, I promise. I got really into working with cardboard as a construction material. It's got some really excellent properties. It's dirt cheap, you can find it everywhere. And you can build some surprising mechanical objects with it. Probably not to everybody in this room. And so I started working on some walking robots as well too. Eventually built a couple of little 6-legged walking robots out of cardboard. Which then brings me to the start of my own machine design adventures. So I brought a bunch of these cardboard things to this place called Othermill that I'd been contracted before and had stolen the laser cutting from. And the lab director had this idea for a project to build a low-cost CNC machine that could do most of what a laser cutter could do at 1/100th of the price. And the idea was that this would go into schools and like kids would get the experience of doing digital design and manufacturing in like at a much earlier age. So instead of waiting until like college, like they would understand like they get the full experience of making a thing with a machine using a computer. And the project was called Mentor. And the lab's kind of a weird place. It's an old pipe organ factory. And it's run by Saul Griffith. And make a lot of strange things there. It's like inflatable robots and CNC machines and weird bicycles. So this is my third machine, and I designed it with a guy named Jonathan Ward from the Center for Bits and Atoms at MIT. And he was part of the Machines at Egg program. And one of his many interesting contributions to the world of machine design is he figured out how to cut a buckle snap feature into the frame of the machine, so you didn't need any fasteners. So this is all held together with little flexural elements and pin locators. You build up your structural loop this way. The structural loop in CNC machines is the part which connects the part being worked on to the part doing the work. And it's very important. So Jonathan designed the frame, and then I designed the cutting head. This is pretty embarrassing. This is my first attempt at making a vibrating knife cutter with a rotating head. And it's made out of Delrin. And because I had been playing with flying robots, I used a bunch of Hobby King hardware to get it to work. And there are many, many things wrong with this design. It vibrates at around 200 hertz, so it didn't last very long. But eventually, it got to work, and this is one of the most exciting things that I've ever made in my entire life. And it is a circle that I cut with a machine I designed. It's a pretty great feeling. This cutter is a 4-axis machine. So unlike a drag knife cutter that's like a vinyl cutter. It takes a 5-cent X-Acto blade, it vibrates into a very high frequency, and fourth axis turns the X-Acto blade to travel in the direction of the cut. And what this does is it drops the cutting force dramatically. It goes from like, I want to say it's tens of kilograms down to like micrograms, all the stuff involved. And I can do this with a surprisingly large number of materials. And one day I went to the lab director and I was like, hey, so the software engineer she promised to write this interface, when can we get started? My background is that I'm a software engineer, worked at Apple for 9 years. He looked at me and he's like, well, they're busy. Suck it up, princess. And so I retired from being a software engineer and started working on an interface. And I remembered like my frustration with all of the other CNC machines that I had used prior. And I wanted to do something very different. I wanted something where a novice could sit down next to the machine and the machine could tell them what it thinks it's going to do. And this is completely novel in any CNC system that you will run into out in the industry, with some very rare exceptions. I started with this cutter, and this is the first boot up of it connected to the machine. And you can see the JSON control channel running down the side there. One of the things that made this possible was a USB-based CNC controller called TinyG, which did not require a parallel port, and took raw G code and did all of the pulse train translation. So it cut out a huge chunk of the system normally needed to control the drives. So we kept iterating on the machine. It got slowly better over time. Eventually, it started having things like a metal in it. And we started cutting out more complicated things. And along the way, we discovered that it could do more than a laser cutter could do. These are 3 different materials that you really can't do on a laser cutter. The first one is industrial felt. And if you do cut industrial felt on a laser cutter, it smells like burning sheep. It's horrible. It will cut it, but you will not want to be in the building for the next week. The one right below it is polyvinyl chloride. And it's a PVC fabric, and it's what we make the inflatable robots out of. And then the one at the bottom should get everybody who knows an architecture has ever been in architecture school extremely excited. And that is a light foam core, which you cannot cut on a laser because it melts and catches on fire. And so what I learned is that all architecture students, when they are building their models, will sit there with an X-Acto knife, very carefully cutting all of the little corners. It's the 21st century. It's one of these. The interface got better over time. You can now drop images and stuff on it. Sort of playing around with sort of like coloring schemes. We took it to Maker Faire, showed it off to people. On the far right is a friend, Forrest, who writes all of our motion planning code. And he had the Herculean task of trying to figure out how to get a 5-cent X-Acto blade to accurately cut within, we used a 10th of a millimeter as our target, on a machine made by at least one amateur machine designer. And so it takes into account the entire prioritized geometry of the blade, the tip. And so you get to the end of a cut, it'll look the blade up, flip it all the way around, and finish the cut and come back, which is a pretty interesting control scheme. Unfortunately, somewhere around 2013, Congress decided that education programs in the military weren't really all that great, and sequestration rolled through, and we lost our funding. And so this project that was slated to have $3 million of funding and take us in manufacturing was now dead in the water. And we were scrambling pretty hard to figure out what we were going to do. And so my business partner, Danielle, and I panicked. One day, while we were in panic mode, we went downstairs, and Jonathan had this tiny little 9-inch by 9-inch by 10-inch milling machine in it, just as a hobby piece. And he designed it to cut out little surface mount circuit boards for people who make guitar pedal effects for himself. He's a pretty good guitarist as well too. And I saw it and I was like, wow, this thing's amazing. I want one, and I know 50 other nerd friends of mine who probably want one as well. So I went to the lab founder and was like, hey, Saul, can I have $50,000 to launch a Kickstarter? And he was like, sure. And,
Works every time.
Works every time. And this is where we get to machine number 4. And the reason I've labeled this machine number 4 is that when you see a product that's like sitting on a table, there is all this other machinery that has to come up around it to bring it to market. And a lot of the big trouble that like people get into when they first start a company, first start doing product design, is they forget about all this other support machinery that needs to come into place. And it's everything from like your supply chain to your contract manufacturer, to your HR department, which keeps paychecks showing up on time. Like it just goes on and on and on and on. The factory design itself. A factory is a machine which builds products, and you have to design it. You have to design it in tandem with the product that you're trying to build. So we get to mistake number 1. This is how far we were when we launched this Kickstarter. I had Jonathan's mill and had the other cutter and my control software. And so in the months leading up to, I think it was 3 months leading up to the announcement of the Kickstarter, we sprinted towards getting a working demo that we could show off to people. And this was as much as we had when we first posted that. And that's a CAD model. Raise your hand if you think a CAD model is a prototype. And this is how well the machine was cutting. Had a bunch of problems. Jonathan is an amazing machine designer. His specialty is coming up with new classes of machines. So he's got some great stuff he's building. And the design of his machine, he builds them for himself. And he once told me that the MTM Snap, the flexure element, was an exercise, it was a joke, to see if you could make a CNC machine that didn't have any fasteners in it. Basically, never intended to be a part of any shipping product. My inexperience as a machine designer didn't know this. And this is as far as the software I had gotten when we launched. I had it rendering a version of the Othermill and showing preloaded G-code paths. We didn't have any motion planning. That all needed to be written. Didn't have board import, didn't have SVG import, didn't have, all it did was show you where the G-code was probably going to go. But eventually we got it to work, and it's got cropped, but the machine started to perform a little bit better, and I had some close friends of mine helping out who were early Kickstarter backers. And this was Arduino, which is made by, it's an Arduino Bart map shield made by my friend Star Simpson. And we won some awards, took our Jonathan's mill to make it fair. Got board import to work. That's an APM, so the Arduino autopilot for flying drones. And spent some time trying to figure out what to do about the fasteners. Sometimes, in product design, you think you could, like, there's room to be innovative. And I was trying to figure out if we could still make this with like little pin fasteners. And other times, it's just like, just do what everybody else does. It's probably a reason for it. Went through a bunch of different revisions of spindles that were breaking pretty frequently. And up until this point, all the machines that we had built had been cut out on a early 80s era 8x10 foot gantry crane. It was a 5-axis gantry crane with 3 working axes. And when it would boot up, the heads would rotate around and it would try and locate all the rest of the axes and it would go out of true. And then you'd have to sit there and you'd have to realign it before you started the day's job. And we're like, we're going to go into production and try and make this thing and have customers, like something must be done. And so we ended up replacing it, and we we just bought ourselves a big giant Haas Gantry router. And all of the frame is cut in one pass. Well, this version of it is all cut in one pass from a single sheet of 2 by 4 foot HDPE, which is high density polyethylene. And it started to take shape. And we're getting pretty good performance results. So this is a piece of the FR1. You can see a banding on the side here. And that banding is 5/1000 of an inch of copper shaved off the top of your top of the circuit board. And I forget how thick it is, but there's basically about a half a thou less of copper on the top of the board there. So this is displaying very, very good depth control. And if you measure it, it's the difference between half a 10 thou on the nice Toyota calipers. But to figure out wiring harnesses, CNC machines are pretty awful. Like a computer, all of your wiring is down in the case, and CNC machine has to route all over. And trying to communicate with manufacturers, we knew that we didn't want to do the wiring ourselves, but we get manufacturers to do it. We built a bunch of prototypes, and all the while our backers are continuously being like, "Hey, it's been like 6 months. What's going on? You said you were going to ship in September of 2013." That came in. And I learned one thing very important, which is that when you launch a Kickstarter, you're not trying to find your first customers. You're trying to find your best customers. The purpose of a Kickstarter is to find those people who, against all odds, believe that the thing that you're trying to do can actually happen. And once you've identified them, the worst thing you can do is not tell them how you're doing. And being that I came from Apple, I made some pretty big mistakes in the first 6 months. And eventually we learned that you can as long as people see that the finish line is approaching, they can be pretty forgiving with some horrible schedule slipping. Performance on the machine got better. This is a section of the surface of the moon cut out at 5 mil spacing. Pretty good. Shows it there. And then along the way, we discovered that in trying to bring our product through CE certification, NRTLs, probably all had to deal with them at one point in time. As a software engineer, I had never had to deal with an NRTL before. So this was quite an eye-opener for me. And we brought our product in, set it down on the engineer's desk, and it took us 3 months for us to get our NRTL, what we liked, to agree what the machine was. Because you're all familiar with NRTLs. The process is that you get lumped into a certain category, and it's a combination of what the machine is.
I'm not familiar with that.
Oh, so the way this works is,
what is it?
An NRTL is a nationally recognized testing laboratory. So UL is an example of one, Intertech is an example of one, TUV. Whenever you pick up the bottom of some consumer electronic on the other side, you see these marks there. What those marks are for is they're a proxy. You take the way the world works is you take your thing that you've designed to one of these labs and they test it through some globally recognized set of rules that the product does what it says it does and is safe to use for the people that you are trying to sell it to. And there's a match between who you're trying to sell it to and what the machine does. And we found we had a really big problem because we were trying to make a milling machine that would show up in people's homes. And they freaked out. They're like, "This does what?" It's got high-speed rotating things. You can get your fingers caught and get pinched. And so after 3 months, we finally got them to agree what it was. In one very hilarious moment, there's a thing called the Machinery Directive, which describes the rules governing CNC machines in industrial settings. And this engineer on the other end of the phone sends me this link for a safety cutoff switch. I was talking to him on the phone, and I pull up the web page. And the safety cutoff switch is $500, and it's about this big. It costs more than the bomb, costs half as much as the bomb, and is like twice as big as the cutting area of the machine. There's no place for it to go. It's pretty frustrating experience. But in the United States, you only need that for export. In the United States, to sell product, there's only one thing that you have to get it to do. It needs to pass the Part 15 FCC rules, which it did not do. So we had to redesign the controller board for it. Because Kickstarter is not a sales to the public, you can break a lot of these rules. One of the other things that I think catches a lot of first-time product designers by surprise is your packaging is part of the BOM, it's part of the machine, and you really need to think about it from the very beginning. And we thought about it a little bit on the late side. And the box that we first shipped the machine out had some problems where, so the way that you do the package design is you take your machine and you put it in the package and then you take it to a lab, and then the lab shakes it really freaking hard. And this is to simulate what happens when a poor FedEx plane pilot hits some heavy turbulence on a 12-hour flight to Southeast Asia. And it's pretty brutal. Like, I think 15 Gs is somewhere there. And depends on what you're testing. So we ended up with a bunch of broken machines before we figured out what was going wrong. And this gets me to big mistake number 2. Besides not having your prototype ready and designed for production, which was we thought that the thing to do when you want to make a lot of things is to go to a contract manufacturer and get them to do all of the hard work. One of the things that you learn is that you also have to know how to make your own machine well if you're going to communicate to a contract manufacturer how they can make it well. Because there is an inherent difference between how manufacturers build things, which is they want to be very risk averse, and how product designers design things. We can just change one more thing. And we didn't know how to build our machine well, and so it took us 9 months to ship the first 200 machines. Apologies if any of you were in that batch. This is mistake number 3. When you're in the middle of trying to do a product launch, don't try and do a special edition. This chewed up about a month of our time to market, because by just changing the plastic a little bit, it changed a bunch of the other design parameters. The thickness of the plastic was slightly different, which threw off a lot of the tolerances. And so we had to scrap several block frames before we finally got the special edition ones working. So do one thing. But eventually they got out there, and this is the very first thing that I saw from one of our customers. This is like the second most exciting thing I've ever seen, which is something that someone else made on a machine that I helped design. It's like, I think it's super adorable. And by this point in time, we managed to dial things in pretty tight, and we're getting really, really excellent performance out of the machine. And there's this thing about machine specifications that you'll see out there in the world, and you will almost never ever. Does everybody know the difference between accuracy and precision? There's a lot of non-knowns. So you'll almost never see a machine out on the market tell you what its accuracy and precision metrics are. And the reason for this is that there's a huge, huge number of variables that will determine performance envelope under a wide variety of cutting materials, metrics, experience of the machinist, how well the machine has been maintained, and so on and so forth. So our advertised specs are plus or minus 1,000 per page. And that's a number with our machine that you can hit every single time. There's a shall not be named Japanese mill manufacturer that makes tiny mills. And if you pull up their webpage, one of their metrics there is machine resolution, and it is, let's make this right, 0.0000187 millimeters, which is 187 nanometers. That's well into the thermal effects. So as the sunbeam hits the machine, it's going to get thrown out by like 10 times that. So we started like now the machines were shipping and we were working on getting the V2 machine out. We had some time to like experiment, push, figure out what the thing could actually do. And so my hardware manager, Sam, cut out this carbon graphite glass mold, which was pretty cool. That's what the machine looked like after it was done. Took a while to clean, but it's carbon graphite block. It's got pretty good surface finish. These are for some glass eyes. And then a friend of mine, who was one of the Kickstarter backers, sent me this one day. And that is a glass wafer with 20 microns shaved off the top of it, cut on the V1 Othermill. And frankly, it kind of blew me away. He's doing microfluidics research. And he said the machine was accurate enough that we no longer had to go down to the shop and use the like $300,000 super high precision like glass cutting machine. So he could just like sit it on his desk and like he built a custom vacuum shop to hold everything flat and put like a tiny bit of like diamond cutting lube on there and then just waited it for it to finish. So I hired him. And he's now our lead mechanical engineer. This is another fun anecdote from production. Somewhere around the middle of the production run, we got our once-a-year lightning storm rolled through San Francisco. This is like 2014. And lightning sent a huge power surge running through the mission where our workshop is. And all the power went out in the middle of the machines running. This is a terrible thing to do to high-end CNC machines. Because I learned that they do not have built-in surge protectors. This is a thing you're supposed to purchase and have installed in the building. So when we booted the machine up the next day, after the power came back on, our $40,000 Hitachi spindle was dead and would not turn. And apparently what had happened is over time, the fan had been running, had a manufacturing defect, and the lightning strike took out the fan stopped running, and bearings heated up and froze. Which is super fun. And so what this is that's Alana, who's our head machines, and she's doing a tolerance check on some X-carriage frame pieces that we did the final machine on another mill. So this is a V1 Othermill making V1 Othermill parts. I always get asked this: can you make a mill with the mill? Like this, the whole machine inception thing seems to be super fascinating. And so one day, my hardware manager Sam again comes back from vacation and he's made a tiny little Othermill. We've actually found motors small enough to drive the carriages, but we've got other stuff to do as well. And so for the V2 machine, we took a lot of the stuff that we learned from our painful experience with the NRTL and we rolled it into the new machine, so it's fully enclosed. It's got safety switches, spindle lockout, super fun stuff like that. I don't know if anybody recognizes this room. So that's the White House. And we got to go to the White House Maker Fair and mill a little dog tag for your husband's dog. And when you do this, there's a super fun thing I learned is that there's an archivist whose job it is to assign a value to every gift that the President of the United States gets. And so we got this very formal letter asking us to declare what the value of this dog tag was. And what, $5? Which brings me to machine number 5. This is our machine that we're currently shipping and the machine that is back there. And like the major design goals for this machine, based upon my previous experience, was I wanted it to be as simple to use as possible, which is a very difficult thing to do with a CNC machine, especially a mill, as there's so much stuff. And I wanted it to be portable, and I wanted it to be accurate. And portability is not something that has really ever been on anybody's radar, combined with accuracy, for pretty much the entire existence of CNC machines. And once the machine is portable, it completely changes how you can interact with it. Because like normally they're a thing that you go to, like you go to dad's shop, or like, guy down the street, with your friend, and she's got a mill. You go and visit her. When it's portable, like I can walk into buildings with this machine that can hold a sub 1,000 inch accuracy in one hand, like set it down on the table and go to business. And that makes the interaction model that you can have with it in like the home or the office completely different. Right now you can have one you can pass it around. Changed a couple of other things on the V2 machine. We found that the plastic bed on the V1 machine it wasn't rigid enough. And there was enough variance in how the metal plate would get attached that people would try and use the corner to locate things, and it wouldn't accurately be reflected in the software, sort of breaking that first rule of making the software show you what the machine thinks is going to happen. So we redesigned it so that the tool can be flipped over and can come around the side and it can touch off on all points and give you full position and orientation of the bed automatically. And for the V2 machine, we also decided to learn from our past mistakes and figure out how to make it well ourselves first. So we bought all of our final assembly back in-house, and we moved all of our machining and manufacturing, with the exception of the frame, out of house. So we got machinists to work with metal to do the thing they do really well, which is to give you nice, accurate parts to your tolerances. And then we figured out how to build our own machine really well, doing the thing that we knew we could only care about, like really only we would be able to care about enough, which is making a really, really accurate and relevant machine. And this is what it looks like today. We're doing batches of 12 at the moment, and we're up into batches of 48 because our demand is far outstripped our ability to produce them. That's probably about as high as we can go in our current space. And another fun thing about Kickstarters is, so we raised like 300 and change on Kickstarter. What a successful Kickstarter gives you is it gives you the ability to go down to Sand Hill Road and ask people for the actual amount of money it takes to start something like this. Like we're very close to getting to the point of break even. It's been about 2 years of extremely hard work. And this is the signatures of the 20 people who were working on the project at the time we shipped our first commercial machine, which was in December of last year. And the first machine that we shipped, laser etched all our names, and it's an homage to the original Macintosh. It's on the bottom. So the title of this talk was 3 printers and lasers and mills. I haven't talked about 3D printers yet. These are my 2 favorite 3D printers. I haven't used them. I'm just using them. I really like this one right here. Most of the time what I do with it is I print out parts for my nieces when they come over. They're just like, yeah, make me an owl. They really like horses and owls. And I get asked this a lot, like 3D printing got all of this attention in the last decade or so. Like, why are you making a milling machine? And I think that what 3D printing did is it really let everybody's appetite for the ability to do manufacturing. It got people very excited about building physical objects, and super explosive. But eventually you run up against this just materials limit problem, which is that like materials actually matter. If you're building real things, they need to be of real matter. So that's a glass plate again. After Joachim came to work for us, made us a nice little glass company. That's mother of pearl and purple heart. That our support engineer Simone made out of actual oysters. And that's a coffee pot for scale next to coffee beans, made out of walnut. This machine and the V2 machine. And that is a microturbine made out of aluminum, which is made by Joachim. So, thank you for listening to me talk about CNC.
I don't care about 3D printing. What about fourth axis?
That's a pretty great idea.
Maybe that's a hint, too. All right.
You didn't talk much about your software. How was that development? Did you do that in parallel? Do you guys have the PC software now, or is it Macintosh only?
It is currently Mac only, and that is historical because I came from Apple and I drew the short straw. But we care quite a lot about having
About the other 95%?
About the other 95%. So that is high on our priority list.
And did you develop the software in parallel, or did you hire it out, or did you?
We developed it all in-house.
Okay, so you hired software engineers and
Yes.
they worked on it as you're working on your prototypes and manufacturing and all that?
Yep. Yeah, we have a software team of about 5 people.
And did you do it all from scratch, or did you use a lot of open source code, or what was kind of your thinking there?
So I've tried to keep as many aspects of the machine and the system as open as possible. When I get to wear the CTO hat and talk to my investors, they want to know that I own something. So the core, the part of the interface, the interface and the motion planner is proprietary in-house. The mathematics library that it's all built on top of is an open source project from another team that was at Othermill. It's called Geode. The firmware that the machine runs on is completely open source. And so if you want to go in and like hack it up or fix bugs around bugs, the firmware is totally available to do that. We'll remain that way as long as we're using that drive controller. Yeah, the machine itself isn't really hiding a lot either. It's super hackable because it's not made out of metal. You could literally like add a vacuum port by grabbing a hand drill and just like drill a hole through your side, which is a sort of fun aspect of it.
What kind of files does the software take? What can you feed into it?
So I knew that designing a CNC machine for the general public was going to be freaking hard, and so I wanted to pick an audience that would be a lot more forgiving, a much more technical audience. So I picked electrical engineers. Sorry guys, you're the guinea pigs. And so it works directly with driver files, doing most of your high-end packages. It also directly imports equal board files. So the current experience right now is like, you want to go drag something in, like you have to like into like a camp program. You have to set up all of your settings. And I tried to keep it down to the point where you have to set up as little as possible. How big is the thing you're trying to cut? What's the board file it comes from? What tools do you have? And the rest is automatic. Trying to find where my board file is.
And so the board that was done with wood and abalone, that was actually done in like Eagle or some other program like that and turned into a Gerber file? Or?
Yeah, we also support SPGs.
Okay.
So, I'm using Skip a lot in house. The SPG support's a little rough. Yes.
You said that you can flip something over to get more accuracy or to get zeros?
To get both sides.
Okay, all right.
Like if you're doing two-sided machining. So machining should really be called fixturing because that's what you spend most of your time doing. Like the part where you cut, it doesn't really, that's like the short part. That's the fun part. We call it CNC TV. Like we have to like yell at each other every once in a while. We're like, hey, get back to work, stop watching CNC TV. As you know, we're all listening over there.
With circuit boards, what's the tracing space?
10.
And can you go smaller? Because you're saying for better accuracy, it's just the size of bits you can get.
I sound like a jerk for saying this. I can go smaller. It takes a lot of experience to kind of really fun stuff. I mean, 10 mils is right at the boundary where we make the entire process completely automatic. Board flatness becomes extremely important when you get below that size or at that size. And it's because if you think about it, the 10 mil across line mils is like 0.01 inches. If your board is popped up by 0.001, that's 10% of the diameter of the cutter. And so it pops up even more than that if it's not properly fixtured. Suddenly, what was just skimming off the top layer of copper is now going to get buried in the bit. And it makes me sad every time a customer writes that I feel personally responsible for it.
Does it have a cooling system, or does it have any sort of?
No, it's all dry chain.
Is it all two-dimensional then?
No, 3-axis full G-code NIST spec. So you can use like
So I
HSM.
said we were talking about PC board and SDG, those are both two-dimensional.
Oh yeah. Those are the ones that we have motion planners for built in.
Okay.
But if you want to do any contouring or things like that, you need to use a third-party camera. One of the things that we've done is work with Autodesk. And if you use their Fusion 360 that has HSM works built into it, there's profiles for the Othermill built in there. So
their software drives your machine directly then?
it doesn't write directly, it outputs standard G code.
Okay, so you can also import G code.
Yep.
I forgot that one happened.
G code SPGs, EVA board files, and
Okay, so I can bring in a G code file and have it do a three-dimensional
Yes.
and tool change and all that.
it'll pick up, I believe it'll pick up tool changes impromptu, but you might have to split it apart at the tools.
Okay,
And then when it gets to the new tool, it will just pause, ask you to change the tool, do the automatic touch off, and we continue with the next part of the job.
so it does a touch off at the start of every file.
So tool locating is on that.
What was the processing cost of doing the testing labs? Was the FCC thing done by the same people?
We did the FCC with fine folks at Atlas.
So that's a different entity, that you
Yes.
specialty FCC?
Yep.
What's the cost to get something UL equivalent? UL is really expensive.
Hideously so.
US FCC is about 10K, C is about 50K, and you can do FCC and medium like that.
Say again, sorry?
In the US, FCC compliance is about 10K, C compliance like full spectrum test about 50K. And then you can go to Asia, you can do C testing, maybe 10K.
Yeah, it depends on where you're going. Japan and Korea are really difficult. They have the 10 meter or 3 meter.
If it's 10 meter, yeah, you don't want to do.
Yeah, it's pretty rough. It's very expensive. I've been inside of a 10 meter testing box, and like I asked if I could take pictures, and they're like, it's like I can fly a plane in this.
So regarding fixturing, how is everything fixturing?
We use a proprietary machining tape from 3M called double-sided sticky tape. You can find it anywhere. People often ask why can you use sticky tape, and it's like, why is the machine made out of plastic? Why did you make all these weird design decisions for the CNC machine? The cutting forces in micrograin and mills are extremely small, and to use them effectively, they take off a very small amount of material at a time. So the machine is designed to resist a 10-pound force. And all of the parameters sort of descend around that. If you make the machine any larger, the rail sizes have to go up, everything else has to get stiffer.
How does it work if you have to flip something over so flat surfaces?
If you're doing like the teapot, the coffee pot. So that's done in 2 operations. You start out with a cube, and you machine the first half along the lines of symmetry, and then you refixture it after it's been flipped over, and you machine the other side. And so for it to line up, you need to know exactly where the blocks are.
So you need a second fixture after you flip it over, because the first fixture won't match up in there.
So one of the things that I've designed into the machine, and it works pretty well, is there's a little bracket, a little metal bracket that's right angle. It's got 2 little holes in the corners. You can see it over there. That gets bolted to the metal face of the bed, and it's also made out of metal. And there's a calibration procedure where we ask the user to flip a bit over so they get the flat back end. And it goes down and touches off on a bunch of different points. And that gets all of your little micro shifting offsets and rotations. If you look really closely at the machine on a bracket that's been mounted for it, you can see that the actual board file is like slightly tilted. And so that's, if you flip it over to the other side, assuming that your material is perpendicular, it's skewed and you get an offset, if it's perpendicular, you'll get the same original on the back side. So that was the methodology that we used to try and solve that problem.
How does the drilling intervals work? You keep the drill bit, or you do triple it?
It's accurate enough not to cut into its own bed.
Are you just the sacrificial layer?
There's the sacrificial layer is replaceable because sometimes it gets sacrificed. It's realignable and replaceable, but the machine is accurate enough that when it's used correctly, the last thing it will do is it will hit the tape and then come back up. So we use the tape as the scope point most of the time. I forget how thick the tape is, but it's really thin.
Don't you get fiberglass dust when you clean the doors? Or
That's why I use FR1, which is a phenolic. Fiberglass is horrible. We have all over our website, we have like, don't use fiberglass. Your mother gave you one pair of lungs. Yes, so that is a problem. What's up?
So, I mean, do people make printed circuit boards out of FR1? I don't even know.
Yeah. I mean, it's just, yeah. So you can buy the material. Since I got the machine, I started buying from them because it's obviously cut to fit their.
What's
their
electrical property?
I think it's cheap
John
Chinese
is
stuff.
good.
A lot of cheap
Yeah.
toys and stuff. It's cheaper than
Yeah, its flame retardant properties aren't as good as FR4.
Which is, that's its main problem, is it catches on fire pretty easily.
Yeah, I mean, at the end of the day, the electrical properties are just going to affect. I mean, it's going to be a different dielectric, right? So your calculation.
FR4 is being crap. So.
Yeah, no.
More crap.
You do RF, don't you? You do RF, don't you?
Yeah, so I mean, it's going to be a different dielectric, but it's something that you can calculate. So you can get your propagation delays worked out. You can get your impedances worked out, and that sort of thing. It's just a different dielectric value. As far as symmetry in terms of dielectric, that sort of thing, that's presumed to be pretty symmetrical. Which from there, then it's just plugging in the numbers, right? I mean, most of the math on that is pretty straightforward as long as you know what numbers plug or where you're plugging in.
So what's the biggest size generally you use?
We ship with an 1/8 inch collet. You can put all the way up to, I believe it's a 1/4 inch in there. And we use a 1/4 inch 6 loop to fly cut the bed flat before it ships out. So the last thing the machine does before it goes out to the customer is it faces its bed flat. This is sort of like the ultimate proofing for whether or not it's true accurate. Like you can, if you see like a rainbow color on the top of the bed, we know that it's pretty flat. We might also run our finger across it and see if we feel anything. And sometimes we have machines that like they don't come out very well. You can see like scalloping in the bed. So it's sort of like the last QC test before it goes out. We can't do very heavy cuts with a 1/4 inch. This is a machine that was designed to go in the other direction. But if you're machining wax or like pipe plates, with machining wax, you can kind of just plow through it. It doesn't really matter what you have.
What's the spindle RPM?
I think the top speed is 15,000. It changed between V1 and V2, and there's a lot of meters, and I'm forgetting which one it is. It's faster. Just scratching. Anybody else have any other questions about machine design?
Last question. How small can you get on the circuit board?
How small can I get? Small size is 8. Chris is trying to.
So I ordered some 6 mil bits from LPKF, and I hoped that they would be here today. They'll be here probably tomorrow. And I'll put it through its paces. I broke one 10 mil bit, which I should have been smarter about it, but I machined 2 boards out today and I haven't broken anything on it. And it's pretty remarkable. I mean, I've owned an LPKF, I've owned 2 Rowan machines, which is a Japanese company that shall not be named. Under all circumstances, I've broken the 10 mil, right? Like the 10 mil just tend to break, and I think it is more to do with how even your material is, more than it is anything else. How close can you actually get it to the surface, and how even we can there's just not a lot of mechanical strength to a 10 mil carbide bit, despite the fact that it has extraordinary mechanical strength for its size. There's just not a lot to it. So.
Cool. Thank you.
So for anybody who's interested on the electrical side of things, actually, so I wrote a blog post just as sort of my introduction to the mill, but the next thing that I'm actually working on are some test coupons, which will actually look at like just electrical properties of what I can mill off of it. So I can sort of calculate, work backwards from what I actually mill off and build some cool little test coupons on the machine that then will figure out what my impedances are, what my propagation delays are, and all that other stuff. So that should be kind of interesting, and hopefully when I'm done with that, I'll blog about it or something. You can read it or ignore it, depending on what your interests are. I qualify in that RF category. Anyway, so next up we've got, first of all, Mike, thank you very much. Joshua, do you want to come up here? We'll get set up. Yeah, we need a converter here. So, oh, sweet. He knows how ill-equipped we normally are because he comes regularly, and so he brought his own stuff.
A lot might be operating system failed.
Oh, okay.
So we'll see.
Yes, we can probably go straight HDMI. So.
That's. Not sure. All right.
So if you have the HDMI connection going here, I think you guys switch that over.
Anyone else needs a beer? Now's the time.
Yeah, if anybody needs the beer, that's
Guys.
What's it? Yeah, you go ahead and grab it.
yeah.
I mean, the ice.
What about it?
I mean, which was melting.
Oh, is it? Yeah, if you don't mind grabbing it, yeah. Hand it to me.
Hand it over.
Cool. Are you cool? You're all mic'd up? Okay, cool. Because we're going to stream this out over the internet. Everybody else.
We already are. Right here.
We already are. So yeah. It's all right. So for those people that don't know, Josh also writes for Hackaday. Hackaday is a popular blog. Supply frame are the evil overlords that run Hackaday, or that own Hackaday, I guess. But writers like Josh are the people who actually drive the content and actually create all the things that make people go to Hackaday. So I'm super excited to have him talk and to take apart all of this.
Yes, deconstruct it.
Yeah, deconstruct it.
Well, we'll reconstruct it. But.
Yeah, that's fine. That's fine. Awesome. Yeah, if everybody wants to file in, I'll go ahead and let you get started.
Very cool. Okay, everyone, I'm Joshua.
Great presentation, guys.
I guess I'm done, right? Yeah, so this is, yeah, so I do write back a day. I guess during the day I work for a company called Mayfield, which is inside of a bigger company called Bosch. And I make, I guess, throwaway prototypes. That's kind of the way I describe it best. To prove a concept, prove some sort of principle that like this robot base is going to work or not going to work. So yeah, it's been a lot of fun. But yeah, so this is kind of going back and trying to teach myself FPGAs after forgetting and relearning and learning it incorrectly. So I figured that this is a good time to figure it out. And I got far enough that I said, hey, this is pretty awesome. I made something that works pretty reliably. It's independent of the FPGA clock speed. Let's talk about it. It's good for actually moving things back and forth. So it's okay. It's not asynchronous. It's synchronous with an external clock, which is from the SPI, from SPI. So that's what we're doing. Let's get started. Yeah, that's kind of where we're going. Why would you do such a thing? And then what is SPI? Just to make sure we're all on the same playing field. And then topology. So like electrically, what does this actually look like? And then plugging it in, and then the protocol, which is something that we get to define on top of that. And then, so of course, we'll define something like define a protocol. Like where we're actually getting this is, so this is actually not original, like the protocol. It comes from a bunch of mem sensors. It turns out you can read mem sensors and write to mem sensors like pretty much the exact same way. It's pretty much an identical interface. And so what we're going to do is we're going to copy that and then turn that into gates and then get that up and running. So I'll give you a quick example, like what you can do with this. One of them is read encoders. And then we'll actually put the two pieces together. And then if you want, I've got a demo which I can turn on in the back if you want to stay a little longer. And then of course the wrap up. So yeah, okay, so really like what we're doing is we're developing a protocol between a microcontroller and an FPGA. I just want a way to connect like my Arduino to my FPGA. And like there's so many ways you can do this. SPI happens to be just one of many ways. And so like that's where we're going. Get this microcontroller to talk to this FPGA. We want data. We want to be able to send data there and get data back, and we want the data to make sense. I mean that's important, right? And so yeah, so actually figuring out like what's going to go here is what we're going to do. And so like, why would you do this? Plenty of reasons why. One of the cool things you can do with FPGAs is you can kind of expand your peripherals. So if I want to drive 100 servos, I can just instantiate a little servo block in my FPGA, make 100 of those, and then have a way of communicating with the FPGA over a microcontroller interface, so I can actually control it kind of as a slave. So the microcontroller can say, hey, control all of these 100 servos to be all these different angles. So that's one application. I could also read many encoders, and provided that I have a way of actually getting the conversation started between the FPGA and an Arduino or a microcontroller of your choice, you can actually get the data back in a way that makes sense. So yeah, there's many things that you can do by just starting the conversation. So yeah, so SPI, what is it? It's a method for communication. It's synchronous serial. It stands for like serial peripheral interface, and really it's a couple of wires. And so what it looks like is at the top level, topology-wise, it looks like this. It's single master, multiple slave. That's kind of the general purpose, the top level view of what it is. But what we're looking at in this diagram is just single master, single slave. So what is not shown here is an extra wire called the chip select, which is important later. We'll talk about that. But if you had a chip select in this diagram, I could put down multiple slaves and I'd be able to address them separately while they all share the same 3 wires, which are here. When it comes to actually sending and receiving data back, the way we do that is you can kind of imagine like they have this like hula hoop or this ring, and they just kind of switch places. They kind of trade bits. And so going from I'll send over bit 7 at the same time I get I'll get bit 7 back at the same time. The way you do that is with 2 wires, and I can send and receive at the same time. So yeah, bidirectional data transfer. I can send and receive data full duplex, which means I can do it at the same time. And then the frame is going to be, in this case, what I do is 8 bits per data transfer. A frame is just like how big does a single piece of information, or how big is a single piece of information that's relevant to my system going to be. Usually it's in factors of 8, or in chunks of 8, so 8, 16, 32. 8 is pretty common. And then of course, I said multiple slaves supported. So yeah. So what it actually looks like when you start plugging things in, you've got the clock, which is the top line, the master in, slave out, which means that's the data that the slave is sending up to, in this case, the Arduino, which is the master. You have the master out slave in, which is the data that's going out from the Arduino and into the slave. And then you have this chip select line. And the nice thing about the chip select line is that those 3 upper wires can be shared among multiple slaves. And what happens is that if I pull you, and everyone else gets a separate chip select. If I pull that chip select low, if the master pulls that low, then that slave listens up, and everybody else says, "Well, I'm not going to listen." And of course, if that chip select line is brought up, then the slave is high impedance. So it's like, I guess you could say it's like air; it's not connected. And so yeah, that's kind of the overall topology of what the communication interface kind of looks like. So yeah. So if you dive down at the logic level, let's say we're going to pass a byte, what does that actually look like? And in this case, I mean, it looks like this. This is SPI mode 0. It turns out there are 4 modes of SPI, and those modes just define when data is valid, when I should actually read data off of what clock edge. And so in this case, clock polarity and clock phase are 0, 0. This is SPI mode 0, which means that on the rising edge of a clock, that's when I should listen up to the bus and say, this is going to be the data that I want on the rising clock edge. Polarity and phase are referring to, is the clock by default 1 and then it goes low to indicate a clock pulse, or is the clock 0 by default and it goes 1 up to indicate a clock pulse. And then the phase is, should I read on the rising or the falling edge of that clock? So looking at this, like we're just passing some data out from the master and also receiving some data in from the slave. So this is just 1 8-bit transfer. So one thing to mention though is like, so yes, cool, I can pass the byte, but what does that byte actually mean? And that's really, this is really where SPI doesn't go any farther in terms of saying like, in terms of actually defining what's there for you. And so what you need to do is you need to kind of put a protocol on top of that. So I need to have an agreement on what data looks like coming out from the master and what, the thing that's going to receive that is we need to have an agreement on how to actually read that. So yeah, what we're going to do is we need to define this protocol. Like we've got this, we need to figure out what data actually means. However, we can send bytes. So what do these bytes, what do they mean? Okay, so yeah, we got to figure this out. So really like taking a step back, I said, okay, like how am I going to do this? Like I want to have a conversation between FPGA and microcontroller. What's a good interface that I should look for to actually get this up and running? It turns out, so a few years ago, I wrote a lot of sensor drivers. And so that means that I actually read a lot of datasheets. And so after you read a bunch of datasheets, you realize that you start like putting together a lot of commonalities between sensors. And so I discovered that the interface for actually reading and writing into sensors was pretty much the exact same thing. And that was pretty much like, let's actually take a look at what one of these sensors actually looks like. In this case, a MEMS sensor, what you have is a little sensor element that has an A to D. So I'm reading some sort of crazy MEMS magic, and I'm digitizing that value to store it locally on my MEMS sensor memory. That gets sent somewhere in memory. I need a way, and there's this control unit, which is actually taking that value out of memory upon request and sending that back up to the person who requested it, or the microcontroller, which is not the person. So yeah, this is an I2C interface for a pressure sensor. So in this case, reading means I'm getting data out from the chip, and writing, of course, means I'm, in this case, for a MEMS sensor, I might be tweaking settings, maybe the sensitivity of my accelerometer, but really I'm writing data back on this bus. And so what they all end up looking like is the first thing you send over is, am I reading or writing? The next thing you send over is the address, like where am I reading from or writing to? And then the last thing you send over is data. And so you can send over 1 byte, you can send over multiple bytes. The cool thing about this interface that I discovered is that if I keep sending more data, the address as to where that data is getting stored locally on the MEMS sensor increments. So first I'll send data value at address 0, and then I'll set the value at address 1, and so on and so forth, as long as I keep sending data over. And then the same is true for reading. If I'm reading, the first thing I read is, say, 0. The next thing I read would be the value at the next address over. And then the next thing I would read would be the value of the address after that. So it's like an auto increments for me, which is really cool. Okay, so if you've actually pulled this out of the data sheet, what this actually looks like over SPI is we can pick out the important things that are coming off of this single transfer. And so in this case, the first thing I highlighted is ignore the waveform, just kind of look at the red stuff. The first thing that we send over is going to be my reading and writing. That's like a 1 or 0. And then the next thing I send over is what is the address that I'm reading from or writing to on the MEMS sensor memory. And then the next thing we're sending over depends on whether or not we're reading or writing. If we're reading from the MEMS sensor, then what I send over, the master sends over is junk. But the data that comes over is the value from that address. If the master is writing over, then the value that gets written over is the value that's supposed to go at that address. And the value that's getting received is junk. And that's just, that's the way it works. So this is for all Bosch MEMS sensors. You can go to any data sheet. So it turns out that that's the exact same thing for indent sense sensors. Like it's pretty much, it did not change at all. So read or write, the address and the data. Same thing.
Bit 6.
Bits, that is, so that's, what is that? I think it might be master or slave.
So like you get multiples on it.
It might be, what would that be?
Is that for chaining 2 addresses? Maybe?
It could be. Yeah, it's a good point we're bringing up. I'm not super sure. It might be
close enough.
But it's close enough.
Yeah.
Like what they've actually done here is they've limited their address space because they're not using the full address space in the previous value. So so you can get up to I think 127 or 128 unique addresses because that's I guess packed into 1 byte. Over here, I can only go up to what is that 128 divided by 2, so 64. I can only hit 64 values in that thing's memory. But again, like the next thing I would be sending over would be the data. But yeah, good point we're bringing up. And then of course for Estee, it's the exact same thing. Read or write, address, and then the data. And in this case, they didn't actually give me a picture of the waveform in the data sheet, but they did tell me that this is what's actually going on in the waveform. So it's pretty standard with what we're about to do. Building this thing up is not in any way particularly a jump out. Like, people do this. I felt good about that. So yeah, that's kind of like, that's like step 1. So now step 2 is actually, let's get an example about what we're about to do, and then let's build it up. So yeah, let's start by like an example application, which would be reading encoders. So let's say I have a quadrature encoder that spits out a waveform, and I need to be able, it's incremental, which means I need to always watch what's happening on this encoder at any moment in time. Otherwise, if I ignore it and do something else, and the value changes, it won't tell me whether or not it's actually going to change. So if I have a piece of dedicated logic that reads that, I'm good to go. So that's kind of the abstraction I'm putting over it. So you have some sort of state machine that just reads encoders. And this is living inside of, this is logic that lives inside of the FPGA. So let's say that out of this logic block, boom, I get encoder data. So now what do this is all living in the FPGA. Where does this data actually go? So a nice place to go would be memory that you synthesize into the FPGA. So we can stick it at address 0 and let it live locally there. And every time the encoder data gets refreshed or rewritten, it's going to get a new value is going to get put there in memory. Okay, so now actually getting that data out, we need to build some sort of SPI interface so that a microcontroller can come along and say, hey, if I wire myself up here and write address 0 over, and then the next value I'm going to get over is my encoder data. Yeah.
Does the encoder just write to a single address, just over the top of itself?
Yeah, it's going to just keep right.
So like 01 would be a different encoder than 0.
Yeah, for sure. And like I didn't specify the width of this. It could be, these could be 16-bit addresses, it could be 8-bit addresses.
It's just incrementing or decrementing the value, right?
Exactly. Exactly.
The number's getting bigger or smaller in that one.
Yeah, right.
Exactly. And really, if you were to do this in a way more fault tolerant way, you might want to have double buffering. So I like stick in the new value while I read in from another one with the previous values. This is kind of like a top level abstraction as to what's happening. You've got sensor data, it's going somewhere in memory, and then I have to get it. And so the way we're going to get it is over SPI. So yeah, so we need to build these things. And so let's do it. All right, so we have 2 parts. We get the controller hardware, and that's going to send commands over to the actual SPI bus. So starting with step 1, let's actually, what does the bus look like? And we'll put it together. So from top level, this is what it looks like, and don't worry, we're gonna like chew at this one piece at a time. But really, like the general idea is this is actually not all that complicated. It's two shift registers pretty much. I have, and I could do this with just one, but I decided two might be a little bit easier to work out. But again, remember that on SPI, we're kind of trading 8-bit values. And so in this case, I have one for saving the received value and then for preparing the value that's about to be sent out. So if you look a little closer, you've got master out slave in, which is going into the input of this shift register, and then master in slave out, which is going to be clocked out. And then one thing to keep in mind is that this is an internal logic. This lives inside of the FPGA. The pins on the outside in pink, those are actually the physical pins that the FPGA is using to connect to the microcontroller. So yeah, so the way this all works is with the magical D flip-flop with the asynchronous load. And so let's kind of figure out what this thing does so we can kind of understand how we chain these things together to make them do something. Okay, so the D flip-flop with the asynchronous load, behold. The nice thing about this is, so a D flip-flop, what it does, it stores 1 bit. You can hold on to that value and keep it. And the way I can actually change that value is in 2 methods in this case. I can either pulse the clock and the value of D gets copied over and stored at Q, or I can assert a value, assert 1 at the A load, and the value that's living in data will be copied over to Q. And so really what that looks like is method 1, I send a clock pulse, and at that positive edge, the value that's at D is going to get copied over to Q, and only at that edge, until I get the next edge, and the value of D gets copied over. So cool, that's method 1 for storing data. Method 2 is with the asynchronous load. So if I assert a 1 at the A load, then the current value living at data is going to get transferred over to Q. So whatever is there, and as long as A load is high, this basically becomes transparent. So data just gets flushed over to Q. So yeah. Once you have one of those, I can chain 2 of them together and say, hey, you know, D, if I give these guys both the same clock pulse, I can build up, I can have these guys shift over their value 1. And if I do this multiple times, then I can shift over 8. And so if I do 8 shifts or 8 clock pulses, the value all the way at the beginning can get all the way over to the end. Or if I'm putting new data in 1 bit at a time, then I can, at the end of the day, store an entire byte. So that's the 8-bit shift register. And so that's actually for sending data. So what I want to do is now, what I can do is I can use my A load signal and say, boom, I'm going to load this entire thing up in parallel. And then as I use my clock pulse coming out from the microcontroller, that's what's going to allow me to shift these values out 1 at a time on the bus. So that is for sending data. And so the other thing is that, so sending data, receiving data, turns out is pretty much the same analog, but kind of in an inverted sense. What I'm going to do is then I can load the value onto Q in parallel, and then I can shift it out serially. So it's kind of the opposite of what we just did. But that's pretty much it for sending and receiving over SPI. So if I want, so now I have the ability to transfer and receive a single byte. But then again, now we need to do something intelligent with it.
Yeah, don't you also need like a counter to know when your data is valid, right? Like address comes in 8 bits, it's not just shifting arbitrarily large streams through, it doesn't actually help you know when data is good.
For sure. And that's actually, so that's actually right there in the corner with the multiplexer. So if the chips line gets low, the clock signals are now valid. But then I think you're hinting now at like, now that I can, are you hinting now?
Well,
that,
so you're gonna, right, chip select goes low,
okay. Clock
becomes valid. The data isn't actually valid until you have 8 clock pulses.
Exactly, yes, very right. That's what the controller actually does. So that's coming up right now. So here we go. So now there's this, I need to know when I'm supposed to set new data on. That is also another controller thing that the controller is going to do. And so we have a way of getting data, holding onto it. We don't know when it's valid. We just have a way of holding onto it. So yeah, now we actually have to pull that out when it's the right time. And so to do that, we need controller hardware. And so this thing is going to intelligently control the stuff that's coming in and out of SPI, the bus. Okay, so what this thing does, it lets us, it generates an address so that we can actually output our data to a location in memory. And then it will increment that address if multiple bytes are sent over, just like the MEM sensors. And then one of the things that we can do at the external level is, let's say we have an end application, like we want to read encoders. We can map that address to an encoder value. Or if we want to do the opposite, we want to control a servo, we can map that value to a servo value. So let's say the servo wants, let's say we have like a hobby RC servo, we want to actually drive that to a particular angle. you can hold that value, store that value as an 8-bit value inside memory, and then wire that up so that the servo will read that 8-bit value all the time. So that's kind of how you would extend this to actually do something with it. Okay, so the controller, if you take one step in, you have something that's interpreting the bytes that are coming in, and then a way of reading and writing to memory. And then again, like I mentioned earlier, these features are being mapped out to peripherals. And this is kind of the way you would configure the peripherals with memory. So now let's actually pop open the Byte Interpreter to figure out how that works. Okay. So what this is going to do is going to figure out, okay, what is an 8-bit? When is it getting the transfer? Am I reading or writing? And then if I'm reading, I need to get the data. And then if I'm writing, I need to set that data. The next set of 8 bytes or 8 bits that you're sending over, I need to set that somewhere. Okay. So if we look at the waveform again, we're gonna build this up from the gates. And the easiest way I figured would be to kind of bounce back and forth would be to look at the reference waveform as a reference. And so really, like step one, I need to count bits. And the way to do that would be with a counter. And so this value D to Q, because there's a thick wire here, so it just kind of indicates that it's not just one bit, but it's multiple bits. But what's happening is that every time I get a clock pulse from SCK, then that count goes up. And then if the chip select is inserted at any time, that clears it to 0. And so every time I get a clock pulse, that increments at once. And so this is pretty much a way of counting bits. And so I can count a byte in this way by starting with the bits. Okay, cool. The next step is we need to figure out when the first byte has arrived. And that's pretty much after 8 bits have gone away or have gone through. And then right when that clock edge falls, that's when the moment is valid. So the way to do that is a couple of flip-flops and then a counter. The counter counts up. It counts starting at 0, goes up to 7. And then between these two flip-flops, it counts the value 8 on the rising edge and then 8 on the falling edge. And so this byte out control signal is valid at the period of time where it's highlighted in red. So that's when the signal is valid. Okay, so now we have this signal called byte out control, which tells me when the first byte has been passed. So what we need to do is then do something with that. So now we know when a single byte has been transferred. Now we need to grab the starting address. And so to do that, it's not that bad. You can actually grab it because it's being stored in that bus. We can stick it into this value here. So I would say focus on the thing in red. The surrounding area is a way for incrementing the address, which we'll talk about later, if I get multiple bytes. But what happens is that on this asynchronous load signal, the byte out control, which tells me when my first byte has been triggered, is going to say, hey, D flip-flops, I want you to grab that SPI data and hold on to it. And so that's what this thing does. Okay, so now we got to figure out, am I reading or writing? And the easiest way to do that is really to chain. So this is a latch connected to a flip-flop, and that just holds on to the write generates a write enabled signal. So the value is stored in SPI value of bit 7, which is the value over here. We can grab we have the entire 8-bit value. So if I stick that into this latch, hold on to it, and then clock it over on the falling edge, I'll know when the write is enabled. So the trigger here is kind of like, this is when the signal is going to go valid. Okay. So the next step after that is, of course, if we're sending multiple bytes over, what we need to do is increment those bytes one at a time. And so originally we held on to this, we held on to the current address. The surrounding logic that I said ignore now, that actually does the incrementing for me. So every time, so if you look at the bottom left, there's this byte out neg edge signal. So every time a falling clock edge happens after 8 bits have happened, this value increments by 1. So this generates an address by which we can go get data from the memory if I can continue to send more bytes over and over. So yeah, now we have a way of getting the address out, and we have a way of incrementing it. Okay, so really, like when you tie those all together, it kind of gets mushed together into something that looks like this, which if you look at it from the beginning, it's like, wow, what the heck is going on here? But if you piece it apart, it kind of makes a little bit more sense. So one thing I'll mention is that there's a bunch of different ways you can handle this. One of them could be a state machine. But kind of the nice thing that I liked about this was that it was actually fairly minimalistic, which maybe I shouldn't have banged my head out or so meticulously to actually get this very tiny. But the nice thing is that this is entirely independent of an FPGA clock on the FPGA. That clock signal is provided by the bus and transfers. So yeah, that's pretty much it for the controller. So now that we've done both of them together, we can actually have a conversation. We can go back and forth and say, hey, I can write data over to location in memory on the FPGA now. And I can also read data back from the FPGA. And so that's pretty much it. Put both things together and boom, you're done. So yeah, so now we can get data back and forth. And so, I mean, one thing that might be worth thinking about is like, well, what the heck can I do with this? Like, why is this like important? Like, once you write it once, you never want to write it again. And so yeah, if that happens to be the case, you can actually just download it. I posted it on GitHub. But really, like at the end of the day, this is kind of just like, this is glue. And so like, now you can actually have a conversation back and forth between microcontroller and FPGA. And of course, there's many ways of doing this, and this is just one way. So that's kind of brings us to the end. And of course, yeah, feel free to go ahead and download a read example. Read just grabs the, read just reads encoders, and the write just writes values to servos. And the way you do it is over on the Arduino side, you say write reg value, and the servos are mapped to address 0, address 1, address 2. And then the same thing with the encoders. The encoders are mapped to address 0, address 1, address 2. Those are actually 16 bits. You have to read 2 values and then OR them together. But that's pretty much it. So, yeah.
How many or how much logic space does this take in an FPGA?
Very little.
So like how many could it theoretically put into like a LX9? Like a shitload?
Yeah, basically.
Metric.
Yeah. Shit ton. Metric shit ton.
Yeah. Yeah.
Did you write some Verilog or?
Oh yeah, it's a good question. I didn't go into the Verilog or the HDL. I did do it in Verilog. And so yeah, feel free to come by afterwards and like we're welcome to take a look at it. Or
you instantiated the gates in Verilog essentially?
Correct. Yeah. So I guess the capture or like the schematic capture of going from this to gates was done in Verilog. But really, like I think so. Getting back into this it was simple enough that I could actually sit down like with the back of a napkin or back of this paper and actually write it out and say, like, hey, yeah, that actually looks like it could work. And then going in and kind of just describing it, it's language independent, really. That's yeah.
How do you isolate the SPI controller and the encoder access to memory? They don't.
Yes, good question. So right now, if you could get a metastability issue if you snapped and hit them both at the same time. You wanted to grab data from there and also wanted to change it at the same time. So that's a problem. One thing, so the solution there, and like that's actually not here, but the solution again would be to say, okay, have double buffering, where you ping pong back and forth between the data where you're getting, where you're actually writing to and reading from. So first I write to memory A and then read from B. And then I write to memory B, and then read from A. So there's an issue. There's one issue there, which is you get a latency of one value being written, so you're behind by one value. But if you're reading this at megahertz speed and your encoder is changing values at kilohertz speed, which is fairly common, then it's not a big deal. And your controller could be, or maybe that's also running in kilohertz speed. You've got an ARM and you're trying to like get a joint there in your encoder. Yeah, it's not going to be a big issue for encoders. But yeah, that's good question.
Follow-up question. Is there a reason that you've chosen SPI rather than I2C for this logic?
Yeah. So I chose SPI over I2C because really I think my SPI felt a little bit more simple to kind of create. I2C, you have, okay, it is a little bit more complicated because, okay, let's see. You need the pull-ups. It's like 1 kilohertz. Between 1 kilohertz and 4 kilohertz is valid. So automatically you need to know the time. The time becomes important. Versus in this case, time digital. Right, exactly. And the timer is provided by the external master. And so you can clock this at any speed as long as the logic can resolve within that time frame. So like I didn't have to deal with that timing issue of respecting that my value is going to be ready at a certain time. Yeah, so it's simpler. It's a little bit simpler to create in gates over I2C. And the other thing is that I think SPIs by default can pass data faster. And you can do it at megahertz speeds versus I2C is defined to be kilohertz speeds.
400 kilohertz max, right?
400 kilohertz max, yeah.
What are you seeing sensor-wise? How many what sensors are you seeing? Like you tested certain sensors.
Yeah.
What are you mostly seeing these days?
So I guess if you wanted to like create a servo extender, like a servo controller, like I know you can go to Adafruit, pick up like a 16 servo multiplexer that just drives servos, or you could instantiate one here. And I was able to do I was limited first by the number of pins that the FPGA had, first instead of the logic. I was still at like I think 10% usage at most. It was well under 10 on a cyclone for instantiating as many possible servos as I could. I ran out of pins a lot faster.
Yeah.
And then for reading the encoders, that's just a pretty quick state machine. You could get well over 100 and not really be taxing it.
So where's your 20-leg robot?
What?
Where's your 20-leg robot? Why haven't we seen that yet?
So yeah, that would have to be coming up. Yeah, so this is my first step in to be like, hey, I can do something. I can have a conversation with my controller and FPGA to actually make it easier to do something after I farmed it out to the FPGA. I can actually control it. So now I got to do something cool that actually involves a bunch of these.
20-leg robots.
Yeah.
So does the protocol here have a variable number of bytes in the messages, or is it fixed? I didn't see a spot for the length.
In this case, 8 bytes is going to is the smallest value that makes sense. You could receive data back or send data over that was 16 bytes or 32 bytes. But a frame is 8 bytes.
It's
You were totally right.
Yeah, but that's even very slow. You can drag out 1,000 bytes if you want.
You just keep clocking it.
You just auto
Right.
increments, yeah.
Yeah.
How would it know where it ended? It doesn't.
On the chips.
Yeah. Yeah, but if you keep going, it'll just auto increment the address until.
Actually roll over.
What's your
Right, so
address?
if you wanted your frame to be bigger, then over here, instead of counting up to 8, I could count up to 10 or 12. Usually, what you run into then is that that's kind of ill-defined in the microcontroller world. You want to count up to some multiple of 8, just because that's how everybody else is kind of doing their thing.
Yeah, but the data sheet will tell you this uses 8-bit frames.
8-bit frames, 32-bit frames. Yeah, and then one other question another thing worth mentioning is that the address space. So I would be able to control up to 127 servos with a single transfer over, or transferring one single byte over, which is like this thing right here. But of course, I could extend that if I wanted to and say, hey, the first 2 bytes is going to tell me read, write, and what address. So it's not that bad to extend.
The thing I've run into in the past is like if you have multiple sensors or multiple slaves, is that when you do want to, if you have a string of 127 that you're talking to at one time, and you just want to talk to number 56 over and over and over again, usually the way it's written, you have to send all 127 each and every time. And the overhead of that is like such a huge crap hole of a problem that like you almost want to write like a single.
That's implementation specific.
What's that?
That's your sensor.
That was, yeah, you're right. It was an ADC, and it was
Yeah.
like it was very specific to that. But it was like that because it was like the whole string. You had to send the whole string every time because of the protocol.
Oh, yeah.
It was terrible.
So every time you had an ADC that every time you wanted to get
It was,
data.
it was like a 4-byte thing. Every time you wanted to send, you had to send.
So there's no random access.
Right.
Just
Exactly.
serial.
Yeah.
Even like the ST accelerometers, you can turn off auto increment.
Oh, you can.
So you can set it so that it'll actually do it so it's just on the data registers or just.
Yeah, like a multi-string, like a stream mode, right?
So it's nice, like when you're first setting up the chip, you go, here are all the settings.
Well,
You
the
just
thing about ST too, the address actually changes if you're going to do sequential reads.
Right.
If you use one address, you're just going to grab a value.
Oh, maybe that's
Really,
well, but it's
another
not
address to grab
Vasquez.
sequential.
Right, so that's on IQC.
Yeah, look here.
That's a SPI.
If it's a single or sequential or multi or single or multi.
Yeah, single or multiple.
Yeah,
That's the MS bit.
It's got to be a.
probably.
Okay. Multi-string.
Yeah.
Cool.
All right.
Joshua and Mike for presenting this week. Again, reminder, if you want a t-shirt with the lovely logo that Alec designed, please come up. We have large and extra large, and that's all we had this week. But thanks for coming. We always appreciate when you guys come here. We love the questions this week, especially like you guys. Great, that's great questions. So please come back next time. We'll have another set of great speakers. If you're interested in speaking, please talk to Matt in the back. We'll probably turn on the Othermill again, make that lovely whine noise of cutting boards, and we'll see you next time. Thanks.
Why not?